Sorry for the delay.
A pleasure.
Some problems with classical computers. So I'm going to talk about quantum supremacy in near-term device, and I guess I should call it maybe quantum advantage in near-term devices, but I'm not sure that quantum advantage means the same thing, so hopefully we'll have time to discuss what we mean by quantum supremacy, and if it means the same thing, that's great. So maybe just think of quantum advantage whenever I say quantum supremacy. But really the main idea of what I want to talk about is how we can use a classical computer, or ideally once our quantum computer gets complex enough, how we can use a supercomputer to check if our classical computer or a quantum simulator or a general quantum computation device is working. So that's the main topic of my talk. So this is the image that we have in mind. So here is our experimental quantum computational device. In this case, this is a dilution refrigerator, and inside we have superconducting qubits. These are my colleagues at the Quantum Experimental Lab at Google, directed by John Martinez. And here we have, well, this is a data center at Google, but here we have a long, really amazing classical computational device that we can use to try to simulate our quantum computer or quantum simulation and use the results of our classical simulation to check if the quantum computer or the quantum simulator is working. That's what I'm going to talk about. And hopefully we can get to the point where the quantum computer becomes so complex that even using this amount of resources, we cannot simulate it anymore, and it becomes really complicated to check that it's actually working as expected. We can extrapolate, of course, from measurements of smaller devices, of less depth, or using less qubits. But when we get to that point where we cannot actually simulate what the quantum computer is doing, but we still have evidence that the quantum computer is working as expected, that particular point is what we call quantum supremacy. So that will depend, of course, on the available classical computational devices. So for reference nowadays, what we have in mind is, for instance, Core 2 is a supercomputer with 10,000 nodes, and it has 64 cores in each node, and it can do around 15 petaflops, at least in theory. So that's 15 times 10 to the 15 floating point operations per second. So it's really an amazing device with around a petabyte of RAM. Once we are doing something which is more complicated than what we can do, we can control it, we can program it, and it has enough fidelity, enough qubits, enough depth, that whatever it's doing, we know what it's doing, but we cannot simulate it anymore. That particular point is what we call quantum supremacy. And that depends, of course, also on the classical algorithms available, right? Which also keep improving. And that's, again, an interesting topic. So to motivate what we're doing things in the particular way we're doing it, which is slightly more complicated than other alternatives, but not too much, I'm going to use this pioneer work from 2012, which is doing something similar, but it's 6-year-old. So it's really a very amazing experiment where they do in an ion trap in a group of immunoblog with Jens Eisert, who is sitting back there. They implement a 1D Bose-Haber simulation, 1D Bose-Haber evolution on an optical lattice, sorry. And in this axis, they're measuring times in units of 1 over j, where j is the hopping term. And in this axis, they measure occupation number in odd sites, and they initialize in the even sites. So because you have hopping of a strength j, you're going to get oscillations of the bosons in the 1D Bose-Haber model, and those are the oscillations that you see here. This is a local observable, and eventually it will equilibrate. So it's a study probing relaxation towards equilibrium. It will equilibrate towards the average value of 1/2. You have a 1/2 expectation of bosons in every site. And they do this for a different range of parameters of u over j, where j was the hopping term, and u is the internal energy of the Bose-Haber model, and also different values of a harmonic potential k. And these are the curves you get. These are really nice experimental curves, while the blue dots are experimental data. And you see a very nice coherent oscillation with an average. They have different system sizes for this 1D Bose-Haber system, but the average is around 40 bosons, and it's half occupancy, so it's around 80 sites or 80 qubits. So it's really quite a complex evolution, and it's still coherent. You see these nice oscillations. And they also compense against DMRG at the regime where DMRG is exact. And you see a nice agreement between the experimental data and the DMRG. And eventually, DMRG, at least at the time for that particular implementation in 2012, kind of runs out of steam. I think they keep track of around 5,000 states in the DMRG basis representation. So the reason why we're doing something different is because this is a local observable. And local observables accelerate, as you can see here. That's exactly what they are studying in this paper. So they accelerate to the expected value, in this case 1/2, and therefore are not sensitive to what's happening at longer evolution times. And what we would like to do is we would like to have a metric that actually tells us what is the fidelity of the whole simulation, what is the system fidelity. And we would like to have the system fidelity not only at short times, where bosons didn't have time to, information didn't have time to spread very far in the system. So even if the system is size 40, it accelerates at around, after like around 4 cycles. So the information didn't get time to spread around the edges. And we would like to get what is the fidelity at, a longer evolution time. So instead of measuring a local observables, what we're proposing is a different way to gather the statistics, right? So to emphasize the point that with local observables, this is difficult to do, I took the liberty to just replot the same data in the previous plots, but I just superimpose them in the same axis. This is time in units of 1/j, and this is the occupation number as before, and I just put the data on top of each other for different parameters. There are other studies in the paper. It's really a good paper that I recommend people to study again. But you can see for this particular observable is that the data, because it's a local observable and it's not very sensitive to complex dynamics, the data sort of kind of overimposes. There are differences, but it's hard to extract the fidelity from here, and especially from here at longer times, but we really like to know how is the fidelity decaying as a function of time. And to emphasize that point even more, I guess, here I'm superimposing sort of a mean field solution. This here is the solution for free bosons of free fermions, actually from a paper from Jens. And I'm just putting some decay lambda, which I'm actually fitting to the data. And you can see that this mean field solution with the fitting sort of follows this particular observable. So what we propose is a similar setup, but a different statistical analysis, which is not using a local observable, because local observables accelerate, and that's a problem. So the proposal is to check that your quantum computer or quantum simulation is working, and to get the system fidelity at longer times is to estimate the cross entropy. So the first thing we want to do is we implement, if you have a quantum computer, you can implement a random circuit, or if you have a simulator, you can implement some chaotic evolution or a non-regular Hamiltonian evolution, which is pretty general. And you can actually see Charles Neal's talk on Wednesday for an experimental realization of this proposal, being the experimental realization that's, I guess, the ground truth. So if we just implement something complex enough so that is sensitive to the parameters that we are trying to program, and it's also sensitive to errors, right? And this is quite general to do. And I will describe how we can check that we have a complex evolution. Then we just take a large sample of measurements. We just measure in the computational basis, similar to what we were doing before, but we actually, instead of aggregating them into average values of local observables, actually in the previous experiments, they were actually aggregating of different sizes too. We just keep the bit strings that we get for every measurement. And once you get the bit strings for every measurement, then we can use a classical simulation like DMRG in the previous example, or maybe the latest and greatest algorithm to simulate quantum circuits in the case of random universal circuits. And we calculate what is the expected probability in the ideal case for the parameters that we're trying to program of the bit strings that we actually obtain in the experiments. So maybe in the experiment we obtain between 1,000 to 1,000,000 measurements. In superconducting qubits is like a minute of measurements. To get 1,000,000 measurements, that's more than enough. The hard part is to do the simulation. And once this becomes the hard part, hard for Core 2, let's say, then we're entering the regime, or what I understand is called quantum supremacy. Maybe you want to call it quantum advantage. But that gives us this real number. It's just the expected probability according to the ideal experiment. And now we just average those numbers. Actually, the log of the number minus the average of the log of the ideal probabilities. And this is a good estimate of the cross entropy. 2 errors of order 1/√, of the number of measurements. So if it's 1,000,000 measurements, it's not a large error. And it turns out that this is basically a measure of the correlation between what you expect in the system and what you actually get. And because we're doing a chaotic or a non-regular evolution, which is sensitive to parameters and sensitive to errors, being able to measure this correlation between the ideal evolution and what you get in the experiment allows you, after some simple normalization, to get a good estimate of the fidelity. And that's the whole proposal, right? So you just calculate these numbers, average them out. You have an estimate of the fidelity for the whole experiment, initialization, measurement, etc. And then, of course, you can do things like extrapolate it to, as a function of size, of depth of the gates, to check that everything is working, even beyond the regime where you can simulate it. And once you go beyond the regime where you can simulate it, you have some experimentally verifiable, in principle verifiable fidelity. That's what we call quantum supremacy. It might be also what people call quantum advantage. I should say that quantum advantage for some people means just a polynomial improvement of a quantum algorithm against a classical algorithm, even if you can do it efficiently, but with a better polynomial in the quantum case. So, as I said, you just normalize the cross entropy. That gives you the fidelity, and that's the number we're interested in. So, how can you try to check if you have one of these chaotic quantum evolutions, non-regular evolutions, which is sensitive to the parameters and sensitive to the errors, and therefore with the cross entropy you get a good estimate of the fidelity. So the simple thing to do is you just, with your ideal simulation that you can do with your supercomputer, you actually calculate for several bit strings. Here is for 200,000 bit strings. You can do it for the whole output state if you want, or if it's possible because it's not more than 50 qubits. Let's say more than 50 becomes hard. You just calculate the ideal probabilities, the ones that you're going to need for the cross entropy, and you just plot a histogram of appropriately normalized probabilities, where appropriately normalized means you just multiply by the size of Hilbert space over which you are spreading. If it is a chaotic evolution, a quantum chaotic evolution, it's supposed to sample quasi-uniformly from Hilbert space, so you spread in Hilbert space more or less in every direction. And a consequence of that is that the probability density of these normalized probabilities, so the probability times the size of Hilbert space, has this very universal form, which is called, well, it's just an exponential distribution. This is a semi-log plot of probability of NP, or probability density of NP over NP, and you see it's a very nice exponential decay. So the exponential decay is red, and here the blue is just the results of a numerical simulation of a random circuit. In this case, it's a random circuit of 56 qubits, 7 by 8 in a 2D lattice, and depth 30 for this particular family of random circuits. And this is the result of doing 200,000 exact probabilities. So if you get this exponential decay, because in chaotic evolutions, probabilities after you're spreading Hilbert space don't work like 1 over n, where n is the Hilbert space. Actually, the distribution of probability is exponential. Then that gives you a simple indication that your evolution is indeed non-regular or chaotic, and therefore sensitive to errors and sensitive to the parameters that you're programming. So there has been a lot of interesting progress on simulations of random circuits, in part for this reason that I mentioned, that if we build a big enough quantum computer with large enough fidelity so we can do circuits of enough depth, then once we cannot actually simulate those circuits anymore, that's quantum supremacy. And here in this plot, I'm giving you an idea of where we are. So this is an algorithm that we published recently related to our previous work, where we map quantum circuits to Ising models, and Ising models give you the partition function of Ising models, give you the probabilities of the circuit, and there are algorithms that have been known for some time to calculate exactly partition functions. In machine learning, this is called variable elimination of the bucket algorithm. So in this axis, we have the depth of the circuit. The different colors are different sizes, as you can see there in the labels. And this axis is time in a semi-log scale. And you can see that basically, and this is the time to get one probability. So if you want to get 1,000,000 probabilities to use your cross-entropy benchmarking, then multiply this by 1,000,000, or if you have 1,000,000 cores, like in Core 2, then just spread it out. This is embarrassingly parallel. So for instance, in our paper from like a year and a half ago, we did all these simulations of 42 qubits or 47 qubits because we wanted to study the approach to the Porter-Thomas distribution or approach to chaos. So we did it at different depths with exponential precision. You will see plots in the next slide. But there have been other algorithms. These black dots are an algorithm from Thomas Heiner and Damien Steger at ETH from Matthias Stroyer group, where they used Core 2, the supercomputer I was talking before. And they did, for instance, the larger circuit is this 5 by 9, 49 qubits, but they did all the probabilities instead of the ones you will need for the cross entropy. They also did 42 qubits. Has been some other paper by IBM. They do, the biggest one I think was 56 qubits, depth 23, and this yellow dot is this plot here, which was depth 30, 56 qubits. So basically the take-home message is, as you will expect, the cost of simulating or the cost of doing the cross-entropy, and by the way, if you can do cross-entropy benchmarking, you can also sample these evolutions because you don't have to calculate the whole state. You calculate only like 10,000 probabilities. That's good enough to sample 1,000. Grows exponentially in depth and also grows exponentially with the different system sizes. And more or less, these are the sizes that we can calculate right now. Although, of course, this we keep improving. Actually, even in our paper, we improve over this by doing a different reordering of the variable elimination algorithm. But that's more or less the state of the art. So if we get, let's say, with 49 qubits, depth 40, which is around here, that's currently very challenging. As algorithms improve, then eventually it will become doable. Okay, so as I said, one of the things we wanted to do is to study the convergence to this chaotic regime, because once we are sort of quasi-uniformly spread in Hilbert space, then we have a very complex quantum state, which is sensitive to errors, sensitive to your parameters, and also is a complex state with a lot of entanglement. Is an interesting place to be. One of the ways we did that is we studied the inverse participation ratio. The inverse participation ratio is just the sum of the probabilities to some power k. So the sum of the probabilities is, of course, 1 by normalization. And the sum of the probabilities square roughly goes like 1 over the number of the states in the support of your quantum state, so 1 over the Hilbert space. And higher powers, if you are in the Porter-Thomas regime, they have a known analytical expression. So we normalize them appropriately. And we see that the inverse participation ratios converge more at the small depths. Actually, they converge exponentially to the expected value from the Porter-Thomas regime. And all of them, all of them actually scratch that. The first 10, at least, they converge more or less at the same time, which is kind of interesting and maybe a bit unexpected. This was actually predicted by my colleague Vadim Smolyansky, and it's probably related to the tallest time, but we think this probably merits further exploration. It's also related to KD signs, but in analytical papers, KD signs tend to converge at longer depths. So this is what we see numerically, and these are 42 qubits done in the Edison supercomputer. And here in this plot, we're showing the sensitivity of errors that I have mentioned several times. So what we do is for different circuits, different sizes are in different colors. For circuits of some size, let's say 5 by 4, which is blue, depth, let's say 25, that's a particular ensemble of circuits of that depth. We drop either a base flip error or a bit flip error in every possible position of that circuit. And then we take the median over the residual correlation measured by the cross-entropy in the previous slide, between the result that we obtain after one single digital error and the result expected in the ideal case. And what we see is that the correlation left is actually exponentially small. It goes like 1 over the square root of the size of Hilbert space. So they are indeed hypersensitive to perturbations, is what people in quantum chaos call these. These circuits, even after a single error, all the correlation is pretty much gone. And that's what will allow you, by measuring correlations, using the cross-entropy or some other method, to extract the fidelity, because you extract the probability of error. Here is a plot where we saw how this works. So this axis is the number of qubits. And actually, we're doing circuits of size of depth 40. And the different colors correspond to different error rates for the 2-qubit gates. In this case, we're control Cs with superconducting qubits. And the blue, sorry, no blue is there. The dots, different colors, different error rates. The dots is just an estimate of fidelity. We're simulating circuits with depolarizing channels after every operation with appropriate error rate. Just by multiplying the fidelities, you get an estimate of the total fidelity. So that's blue. And the squares is numerical simulations with depolarizing noise. Use cross-entropy. And you see that indeed, after simple normalization, the squares, which is the cross-entropy from the numerics, mimics what you would do in the experiment, is matching nicely what the fidelity that you will expect just by multiplying the fidelities of the different gates. Ooh. So to conclude, what do we expect for quantum supremacy or quantum advantage in the near term? Well, what we're trying to do is we're trying to do a well-defined computational task which requires a direct simulation of the quantum evolution. So what we mean by that is we want a complex computational task, is maybe the simulation of a chaotic Hamiltonian or the simulation of a random circuit, something along those lines, that cannot be approximated by a polynomial classical algorithm. And the reason is if it cannot be approximated by a polynomial classical algorithm, then the cost, as far as we know, is exponential in the number of qubits. And this might be different from quantum advantage. Quantum advantage might apply also to cases where there are polynomial classical algorithms, but in the quantum case, you can just do it faster. So this requirement is typical of chaotic systems. So that's why we're focusing on random circuits or quantum chaotic evolutions. Then we have a specific figure of merit that tells us how well we're doing the task, which is just the fidelity. And is the fidelity as estimated by this technique, which we call cross-entropy benchmarking. And this is useful for calibration, as you will see in Charles' talk on Wednesday, not just for circuits, but also for simulations. So we think that it would be nice to get the estimate of fidelity from cross-entropy benchmarking from simulators in other platforms, ion traps or optical lattices or superconducting. So then we can compare, not just the number of qubits, your particular Hamiltonian, but what is your system fidelity, your total fidelity. There is also some interesting relation to computational complexity that I'm not going to touch here. And those are my conclusions, which in the interest of time, because we're already starting late, I will just leave there. Thank you very much.
So we have time for a couple of questions. Meister Jens Eisert.
Hi, Jens. I'm sorry.
Okay, thanks for the very nice talk. So I couldn't agree more that one should think in terms of computational complexity when defining quantum advantages. In fact, my talk will be about this tomorrow. Maybe 2 words of caution when you compare the quantum experiments with classical simulations. I mean, 2 things one should be aware of is that it's like one thing to compare like single plots, and the other thing to reproduce the full functional dependence on parameters and so on. So this may be a more challenging aim. And secondly, the nice thing about like DMRG type computations is that they have predictive power in the sense that they're, at least on the classical side, fully certifiable. Right? I mean, of course, one can ask, do you want to compare 2 non-certified schemes against each other? So that's also interesting. But I mean, in this setting, at least you really know rock solid for sure what you have, and then you can compare it. I mean, that's a nice feature to have.
Yeah, I agree. I didn't hear a question there, and I just agree with everything you said. Thanks.
So last question, just before we go for the coffee break. Enrique, there.
So you're saying that this is a new method of benchmarking quantum systems. How do you compare this with something like randomized benchmarking in terms of how efficient it is to actually process on a quantum computer? Because you're trying to get some kind of fidelity measure out of this, right?
Right, so this is quite related to randomized benchmarking, actually. One of the papers we cite, which was the inspiration to randomized benchmarking, also is a paper which talks about how to do something along those lines, but using unitaries from higher measures. So it's similar, we want to do, if you do a random circuit, then your quantum channels will twirl around, be converted into polarizing channels. And we assume that for random circuits, and we have checked numerically that seems to be the case, then what you expect is the same exponential decay that you see in randomized benchmarking. So that's similar. In randomized benchmarking, you don't need a classical computer because as long as you work in the Clifford gates, at least the typical gate for randomized benchmarking, then at the end you put a Clifford gate that undoes the evolution. And I guess you need probably less measurements because if you undo the evolution, you can just project on the initial state. But there are very similar features. So the main difference is that this allows you, in randomized benchmarking, you normally will do, well, first only Clifford gates normally, and you normally will do 1 or 2 qubit gates, although there are new ideas there to check your whole system, which are also very nice. This is called cycle benchmarking. This allows you to check your whole system, not just using Cliffords, but actually it applies also to quantum simulators. And it allows you to check not only one cycle, but your whole system. And the main disadvantage is, well, you need more measurements, but not that many. 1 million is good enough. The main disadvantage is you need to simulate what you are doing. And that will require a lot of computational cost. But it also has the interesting side effect that once you cannot simulate it anymore, if you can extrapolate your errors, then you have reached quantum supremacy. But yeah, it's very related. And the main difference is to set the whole system, not just individual pieces.
Okay, I think that's enough. Thanks again, Sergio, and to all the speakers of this session.